Okay, cool. Kyber on a potato. So, this is a butterfly. This is, for those of you who are aware of botany, a potato plant. And today we're going to show how to land a butterfly properly on a potato plant like this. In fact, we are going to talk about first FPGAs, because I know some of you are not hardware people or might not spend all their waking hours having to deal with really annoying devices like these. This will not be part of the conference that I'm giving, because I'm going to an FPGA conference, and hopefully everyone there knows what FPGAs are. So first, okay, what is an FPGA? You can say, well, I've got Kyber implemented on my wonderful Sage script. I'm a certain Wouter-Castrix. It works on Sage. Why do I care about like some weird device that you have to program and do weird stuff to? And the answer is the following. If you do Sage, basically what the Sage code does is something equivalent to this. The Sage code will talk to some sublayer in Python. The Python layer will actually then call already precompiled C code. That C code is actually really inefficiently written assembly code, and that assembly code is actually just giving a ton of useless instruction fetches and other operations on the actual CPU, which just burn energy just to do a simple modular multiplication or something like this. Well, really, if you want to save energy, if you want to be efficient, I mean, like in software, you can just write machine instructions, but then still your CPU, the chip that it's running on, is still doing instruction fetches. It's still decoding these instructions. It's still doing fetches from memory. And you're only interested in the modular arithmetic. You're only interested in just doing this one multiplication or this one addition. You're not interested in all the other stuff that's just administrative overhead. So what you really just want to do is you really just want to have like this equivalent where it's just like the guy in charge of just 5 dudes saying, okay, do this addition, do this subtraction. And that's what an FPGA does. So an FPGA is just the logic, not really any of this instruction fetch stuff unless you decide to add it. It is exactly what you want and nothing more. So an FPGA is a big field of circuits. Circuits that can be used to implement things like AND, OR, XOR gates, all your standard things. And these are implemented as lookup tables. So on the chip itself, what you basically do is once you have a lookup table on a chip like this, you can implement any of these, because a lookup table which takes 2 bits as input and 1 bit as output can implement any of these 3 things. You just have to program it to implement one of these 3 things. And so, to implement one of these 3 things, what we want is a lookup table. And, well, if we're using 2 inputs, we might as well go a bit further, because often we have functions that require more than 2 inputs, and we'll give it 6 inputs or 4 inputs. These are usually the standards on most FPGAs. And with these, well, you can implement anything. We also add some flip-flops. These are like memory registers, but these are memory registers for exactly 1 bit. So these store 1 bit, and they only store them for a very brief amount of time. But with these flip-flops and these LUTs, you can build anything. You can build any piece of electronics that you care for. Any piece of digital electronics, I should say, that you care for. Of course, if we're only using one of these, we're not going to get much out of it. So we're going to work with slices, like we're going to combine these things. And we're going to combine them. We're going to add some extra logic for certain cases, because, for example, the people who built these FPGAs have noticed, people seem to like doing additions. So they add a little bit of extra logic to make additions flow very efficiently for these FPGAs. But the basic idea is always these LUTs. And these slices go in bigger things, and these bigger things get combined into even bigger things, and you add some wires in between them, wires that you can configure so that different parts of the chip are connected efficiently, and you add more and more interconnects, and you stack them into bigger and bigger layouts. And then you also add some specialized blocks, which we call DSPs. Now, the point of DSPs is a multiplier. Because while you can implement a multiplier just using these LUTs, it's like multiplication is something that is done so often and in so many different applications. You need it for signal processing as much as you need it for cryptography, as much as you need it for any other thing that you would like to do, that it's really worth dedicating its own part to this. So this DSP slice contains a multiplier and some plus or minus things. DSP stands for digital signal processing, by the way, which is what this is used most often for, but you can use it in cryptography, same as anything else. Then we also have some bigger memory storage, so you can store whatever you want on the flip-flops, but again, they're small, they're not really built for storing large pieces of data. A BRAM can just store a big pile of data and work perfectly fine. Then some more CLB, some more DSPs, and this is what makes up most of the FPGA. So we're not even done yet, because this is, then you have some input-output, but this is just a very tiny piece of what eventually makes up the whole FPGA. So an FPGA is just this copied over and over and over and over and over again. And with this, you can build anything, and you can build exactly what you need to. You don't need to build, don't need to put in anything that is superfluous. So, why do we bother with this? Well, you can't really, on a CPU, if you go publish in, for example, chess, if you get a 10% improvement, that's really good. Because, I mean, you have the instructions for you. There's only so much you can do. You have to do complicated mathematical stuff to get any improvement on, say, Kyber. But in an FPGA, a factor 2 improvement can happen because you're working only on the things that are important for your application. Now, I've been talking a lot about efficiency and why it's so important. Why do we care? Like, why not just run everything on Sage? Why not just grab a Raspberry Pi? You can install Sage on a Raspberry Pi and use that for everything. Like, why would you care? And the reason we care is for two specific things. Sometimes we care about power, and sometimes we care about energy. We care about power if we care about how much energy we're using per second. And in servers and laptops, we care often about power because we have to cool the chip that we're running on. And if we burn too much energy per second, well, on a laptop, the lap of the user will get burned. And you don't want this. You get customer complaints. In embedded systems, you often care about energy because what you're often doing is something like this. This is a Philips Hue device, and what this does is you install it on your door. So you would take that door, you would place this thing on it, and then it will detect if the door is closed or open. And then you can link that to other stuff like lights, like switches, like some sort of detector that tells you if someone is in your house. But of course, this thing is not connected with a battery. Not connected with a power cable. It's a battery. So you place it on your door, and then it should last long. Now, you can decide not to put any security into this thing, and that's very power efficient, because not doing any operation is always very power efficient. But then bad things might happen, which we will describe in a second. So let's decide to put security into it. Well, then it has to be efficient. Because if you try to fit an entire Raspberry Pi into this, well, first of all, it will not fit. But let's say that you do get it to fit. You'll just run out of battery after 10 seconds of installation. And users tend to complain if they have to refresh the batteries every 10 seconds. So you actually have to make it power efficient. You have to make it like really take like tiny, tiny, tiny sips of energy. Because if it just drains energy, if it drains the battery, well, you don't have a product anymore. You just have a bunch of customer complaints. So that was the introduction to FPGAs for people who don't know FPGAs. This is the introduction for Post Quantum Cryptography, because I'm giving this at an FPGA conference, and most of the people there do signal processing and not cryptography. So most of you here know what a quantum computer is. And specifically its impact for cryptography, which is that it breaks a lot of the previous cryptography. And I think it's easiest to illustrate with an example, namely that same Philips Hue light thing that was previously. So this is a Philips Hue light connected to a box. And this was broken pretty heavily about 8 years ago now in a paper by Colonel Flynn and an Israeli university who did a paper called Zigbee Goes Nuclear. And what they figured out is that Philips, the manufacturers of this, had hard-coded the cryptographical key in the device. And you could leak this through side channels. But the point is, once you had the key, you could push whatever software you wanted to this, including stuff that would allow you to, for example, make the light strobe, like flash really brightly on and off. If someone was photosensitive, if they had trouble with, for example, elliptic attacks, you could trigger an elliptic attack by hacking this device. And the only thing you needed was another broken Philips Hue thing close by. So you could just break a city by breaking light per light. So every light would infect the lights in range, inside its Bluetooth range. This is bad, obviously. Like, access to this sort of stuff would give anyone with bad intentions a lot of information about the person living inside the house. It would tell them, okay, this person is awake at these times. It would allow them to, for example, it would allow them to attack them physically by turning the light on and off very quickly. It would allow them to turn the lights off when they were doing a burglary, if they wanted to. It would tell them, okay, this person has just left the house. Now is a good time to search their house. So you don't want this. You do not want these things to be broken. It's also, for the company, it's really bad publicity. So you can fix this by just using cryptography. But if you use the cryptography that's common right now, if you use RSA, if you use elliptic curve cryptography, it's not really going to be safe once quantum computers appear. And you can say, well, it will work for now. I mean, it's fine for now. We don't care. But 3 days ago, Post Quantum Cryptography became a standard. So now, as a company, not only is it a good idea to do so, but if you wanna be in touch with the current standards, you have to do it. And moreover, it often takes like 20, 30 years before stuff actually often devices that go into production. So like you start the design process now. In 5 years, your product is on the market. Your product is going to stay on the market for maybe 20, 30 years, maybe 40 years. You still want it to be secure at the end of those 40 years. So you need to do post-quantum cryptography now. So because it's both a standard and you need to do it for the safety of your clients, you need to implement this. And you need to implement it efficiently, because if you don't implement it efficiently, you don't have a product, you just have a dead thing without a battery. So how do you implement Kyber? Well, Kyber is, for the most part, the main operation in it, and I will not give a full explanation of Kyber, is a polynomial multiplication. So it's just two big polynomials. And if you don't know this, don't worry, because a polynomial multiplication, to do that efficiently, is really just either a Fourier transform or a number-theoretic transform. And if you don't know what a number-theoretic transform is, don't worry about it, because really, like, a number-theoretic transform is just repeated instances of a butterfly. A butterfly is this electronic circuit. A butterfly is a multiplication, modulo some number, and then an addition, modulo some number, and a subtraction, modulo some number. So it's really just these three operations. And really, if you look at these three, well, what is always the most expensive? It's the multiplication. So the real bottleneck of the butterflies, which are the bottleneck of the NTT, which are the bottleneck of the polynomial multiplication, is this polynomial multiplication. It's calculating A times B mod Q. With Q being a constant, which we'll come back to later, and being kind of a nice constant, because there's a lot of zeros in here, which we as hardware designers like a lot. And this is also important, B is generally also chosen from a list of constants. So how do we implement this efficiently? Well, there's a range of solutions. I'm going to now show off my basically butterfly collection. There's a big range of modular arithmetic solutions that people have used, that people can use. And I should point out the reason behind this paper was really having to review a whole bunch of these papers, each of which was presenting its own special solution to this problem. Often this gets like half, maybe a third of the paper space to itself, because this is so important. And everyone brings their own solutions, but not all solutions are equal. So I will divide the solutions in two categories. You have solutions which are basically like you add the modulus until you reach some sort of desired endpoint, or you subtract the modulus until you reach some sort of desired endpoint. And then you have solutions which just substitute things in your operation wholesale. And there's another way of categorizing these. You have solutions that will accept basically any inputs and any problem. And then you have solutions which require a multiplication by a constant afterwards, because they give you a solution that kind of looks like the solution that you wanted, but it's off by a constant factor, which for the problems that we're solving is not always a problem. But let's get to them. So the first solution that's often suggested is Barrett. Barrett is the most straightforward thing of solving this. So as a reminder, the thing we want to do is we have some 24-bit number, which we got by taking A and multiplying it with B. And we want to get this back to a 12-bit number. So 24 bits is too big. This 24-bit number needs to be modulo 3329. And we want to bring it back to something smaller. Now, the really naive way to do this would be to just subtract our modulus from it. So we keep on subtracting 3329 until we get something smaller. But of course, this would take way too long. So we want to figure out, okay, how many times do we have to subtract 3329 from our big number? Well, how many times do we have to subtract? It's basically a division. You just take A times B, you divide by the modulus. Okay, then we have the number that we have to subtract it from. This is just normal division, like just the straightforward way of doing this. Of course, we're not working with floating point numbers. So in floating point numbers, you would do it this way, but we don't have floating point numbers. Those don't exist on FPGA. They don't really exist anywhere. It's just like some illusion that we create to make life easier when you're doing calculations. But when we want to be really efficient, what we think about is, well, this k, really, we can figure it out by pre-calculating 1 over q to a set amount of digits after the comma. And then we multiply this, and since q is a constant, this can be pre-calculated. We don't have to do a division here. We can just store 1 over q in the memory. And we multiply it with our a times b, and then we have k, and then we do our k times q, and then we have the solution. This is simple, it's straightforward, and it requires 3 multiplications. 3 multiplications is actually quite a lot. So one optimization that's got itself a chess paper that someone already realized as well, this is really kind of like, we don't really need to multiply with q, because we know q. Q is a constant. So we don't need to do a multiplication, we just have to figure out, okay, well, q only has a couple of ones in its number. It's a sparse number. So we really just have to shift and add, not really multiply, because this is a constant. It doesn't change. And similarly, 1 over q, we know this. We don't have to store it in memory, we just have to build a circuit that does the same shifts and additions that multiplying with 1 over q would do. And this gets you a really nice reduction, and this really simple idea is already very efficient. Okay. Maybe we can do better, because this idea of like looking at the structure of the modulus, this is really a promising one, right? Like we have q, and for Kyber this is 3329, which if we write it in hex is D01, or in binary it's 1011, and then 7 bits of 0, and then a single 1. So not many ones in here. So when you multiply with this, you just really just have to look at every single one, and those are your additions. So this structure, the first thing, like one of the approaches that people took was, well, okay, so we have, if we go back, we're working modulo this number. If we're working modulo this number, we could say that 2 to the power of 12 is actually equal to everything on the right side of the equation. So whenever we see 2 to the power of 12 in our number, we can replace it by this smaller number. This is a way of making things smaller. So it's the same thing as if you would take 5,000 and you wanted to do it modulo 1001. Well, at first this seems like a difficult problem, but then you realize, well, really 5,000 is just 5,000 minus 5. And 5,000 minus 5 modulo 1001 is easy, that's 0. So really 5,000 is minus 5. And x thousandths is just minus x when you're working modulo 1001. So if x thousandths is equal to minus x modulo 1001, well then, now calculating 5,626 modulo 1001 is easy. You do 626 minus 5. Problem solved. And so you do the same thing here. 2 to the power of 12 is equal to this thing. So you take your number, you take everything left of the 2 to the power of 12, and instead of multiplying it by 2 to the power of 12, you multiply it by 2 to the power of 9 plus 2 to the power of 8 minus 1. And now you have a smaller number, because previously you multiplied it by 2 to the power of 12, and now you multiply it with a smaller number. And if you solve this, you realize that you again have a part that is now higher than 2 to the power of 12, which you can again substitute, and you can again substitute. And you can keep on substituting until you basically just have a bunch of bit operations. Like, you can keep on doing this. This can again get substituted, and you will still get a part that goes over to the power of 12, and it can get substituted again, and it can get substituted again. And at the end, you just have a bunch of additions, and then some final operations. And this is also a pretty easy way of solving this problem. Well, not easy, but once you've solved it, it's efficient. A variation on this theme is the following. You take a look at this number, and you realize, okay, what this actually is it's 13 times 2 to the power of 8 plus 1. So you have this bunch of ones on the left side, and then you have a whole group of zeros, and then you have a single one at the end. Now, this k times 2 to the power of 8, if we had a group of k times 2 to the power of 8, we could substitute it with minus 1. Of course, we don't. It's not easy to see like what our number is multiplied by k times 2 to the power of 8. But we can multiply it with k. If we multiply it with k, it's very easy to see because we can just take all the bits left of 8. So it's 13. Let's say we do 13 times a times b. That's not the number we're interested in, but let's do it anyway. We'll take 13 times a times b. Okay, 13 times a times b, we'll replace 13 by k just for ease. Well, that's really k times every single bit from 8 onwards, plus k times the lower bits. Now, this k times the lower bits, this doesn't improve anything. But this k times the upper bits, well, k times 2 to the power of 8 is minus 1. Since k times 2 to the power of 8 is minus 1, we can just substitute this with a minus 1, and the right part stays the same. And this is a massive reduction because now this is about 16 bits, this is about 8 bits, so we went from 24 bits to basically 16 bits in one step. Now the only problem is here that we've multiplied by k, so at some point we're going to have to multiply by k inverse to remove the influence of multiplying by k. But we can deal with this later, and one of the important things to realize is that in an NTT, you're multiplying with constants, and these constants, these are stored in memory. And if you want to multiply these constants in advance with k to the power of inverse, you can. So really, multiplying with a constant isn't really a problem because you can remove it by multiplying the other thing, the other element that you're putting as input with k inverse. And then I'm going to show one last butterfly, which uses the very same LUTs and flip-flops that I mentioned previously on the FPGA. So we have these 6 to 1 bit table lookups, and these are really the most basic things on an FPGA. These are the most efficient things on the FPGA. All the rest that you see, additions and stuff, that's built out of these LUTs. So being able to use the LUTs directly is the most efficient thing you can do. Now, let's say you don't want to reduce down to 12 bits, but you just want to remove like 4 bits. You want to go from 24 bits to 20 bits. You just want to remove the uppermost 4 bits. Well, these upper foremost bits, you can see that as to the power of 20 times those 4 bits. Now, we can store the reduction of this modulo 3329, modulo or modulus, in a table. And there's 4 possible inputs, because these are, well, there's 16 possible inputs. There's 2 to the power of 4 possible inputs, because there's 2 to the power of 4 possibilities here. There's just 4 bits. And each output has 12 bits. So it's really just a table with 16 rows. And in this table of 16 rows, there are 12-bit numbers. Now, a table of 16 bits, well, we don't have tables of 12 bits, but we have tables of 1 bit with 16 rows. That's a LUT4. So, using 12 LUT4s, 1 LUT4 for each output bit, we can just reduce using exactly 12 LUTs. 12 LUTs is really, really cheap. So with just 12 LUTs, we remove 4 bits. And then for removing the other 4 bits, we can repeat the operation. So every single time, we trade in 12 LUTs for just 4 bits of reduction. And you only have to do this 3 times, and you're there. So, to recap, we've seen 4 different solutions. We've seen Barrett. I've skipped Montgomery because it's not a good solution. It doesn't work well, and it's kind of complicated. But so we've got 4 different solutions. Barrett, which is adding queues, and then these 3, which is substituting some part of your A times B by the direct correspondent 12-bit number. These 3 things work in any situation. This requires a multiplication by k to the power of -1 at some point. Now, how efficient are these? Well, you've got Barrett, which was... This is the thing that most papers will go for. Most papers will go for Barrett or Montgomery, because these are the things that are taught in schools, and these are sort of the standard solutions, because they work in almost every single situation, and with these you can have a changing modulus. But in Kyber this doesn't apply because you're not changing your modulus. These require 90 LUTs. Bitwise is strangely more expensive than this. K-reduction. There are some K-reductions out there, but there aren't many very good ones. And since these two had already been optimized as far as you could possibly go, I optimized the K-reduction as far as I could possibly go. That gets you 56 LUTs, and LUT reduction will get you 72. But you can still do a little bit better, because remember, your LUT reduction will only remove 4 bits. And your K-reduction leaves you with something that's 16 bits. So your K-reduction went from 24 bits to something that is 16 bits. So neither of these things fully reduces the thing. You have to apply it multiple times for it to work. So one thing that you can do is you can first do a LUT reduction and then do a K reduction, because each of the things has different advantages and different disadvantages going towards the very end where you have to do conditional subtractions. So the best thing to do, if you try out every single possible iteration, is the following. You do a LUT reduction first, and then you do a K reduction second. And this will get you down to 49 LUTs. Now, 49 LUTs is really, really tiny. That is half the size of Xing-Adel's state-of-the-art design. With that, you can really run it on a tiny, tiny circuit. So I built this. I've also put this in the public domain, specifically because right now the best design out there, which you can get the open source from, is Xing-Adel's design, which is 90 LUTs. This is about twice as good. And the problem with Xing-Adel's design is that it's not like that there's still some licensing involved. The best really public domain one is the Bitwise design, which was 167 LUTs. So this is public domain. You can just get it from Git. You can put it in your code. You can use it wherever you want. It's effectively yours. And it requires just 49 LUTs. So now, are there any questions? Yes?
I was just wondering why the 4 bits? Why did you choose 4?
So the LUT reduction that's a fairly decent question because I will probably get this in the FPGA conference. So the LUT here depends on which FPGA you work on. So with the Xilinx, with a lot of the Xilinx FPGAs, especially the newer ones from 2014 onwards, this will always be a LUT 6. So it will always have 6 inputs and 1 bit output. On a lot of other FPGAs, such as this one, you get LUT 4s. Now, you can, of course, build a LUT 6 out of LUT 4s, but it's always best to just use the primitive that is on the FPGA. If there's a LUT 4 on the FPGA, use the LUT 4. It's there. And so I've got I made multiple designs for different FPGAs depending on what is best, because it varies depending on which primitives you have. At this point, you're really optimizing this close that it's still better to use K reduction and LUT reduction in every single possible scenario. So like regardless of the FPGA, you should still use K reduction or LUT reduction. But if you really, really want to eke out the last possible LUTs, if you really want to get your circuit down to like the tiniest possible size, then you need to realize what FPGA you're working on and decide. So I keep, in my talk, I keep varying between LUT 6 and LUT 4 because it depends. But I offer both as codes that you can just use. And if there's something else, read my paper and you will be able to design it yourself, hopefully. Yes?
What's the result of the 6-bit LUT thing?
So 6-bit LUTs will give you 49 LUTs. And for LUT 4s, it will give you slightly more. It will get you 83. I don't have that.
Like the results for something more.
OK, then I will change that to thank you. That's fair. Yeah, I should mention that is for LUT 6. That's for LUT 6 on the Xilinx FPGA, and I know that very few people here care, but it's for an Arctic 7. So yeah, 7 series. Yes?
I don't know too much about hardware, so bear with me.
That's perfectly fine. Go for it.
Like any point implemented in software as well. Like, I have code living billions of modular multiplications. Will I get an advantage from using this over, I don't know, Barrett?
No, you will not. Barrett is a good choice for the software. Planter is also a good choice, which I didn't mention. That's another modular multiplication technique. Because in software, you're stuck with the instructions that you have. And so you get a multiplication often in about the same amount of cycles as an addition. Not on all architectures. Like it's going to depend on, like, do you do this for ARM? Do you do this for MIPS? Do you do this for RISC-V? It's going to depend on this. Your mileage may vary. But if you run this, if you do K reduction, then you're going to get into the problem that you've only reduced 4 bits and you've already used one thing. And you can't do, like on an FPGA, doing 7 additions instead of 1 multiplication is a perfectly reasonable thing to do. On a microprocessor, it's very rare that you get to do 7 multiplications because you get to do 7 additions instead of a multiplication, because the multiplication unit is right there.